We are a small, exclusive crowd today. Good to have you here. I would expect that new time, sometime in the future, I won't have to stand here in the mornings and speak to you. So if you don't show up, I don't have to show up. I don't think the deans of the university still is ready to accept that fact, but maybe in a few years. Or at least we could show up, both of us, all of us, and do something differently than me just speaking out in the air to you. Because having recorded everything, maybe you could just as well see those lectures on your own. We don't have to meet up face to face. But this is another discussion. We can have that at the end of the course. We are having it all the time. Let me repeat what we did last time. We did something very important for our little course here. I introduced to you the concept of a confidence interval. The confidence interval is one of the two key tools in doing what is the key issue of this course, that is doing statistics, which I translate many times as looking at numbers in an intelligent way, rather than just looking at the numbers, right? So that is what statistics is really about. And one of the tools to do this is the confidence interval. I gave you the confidence interval for a mean. That is, in the case where we are interested in computing a mean and using this mean to say something about the real world, the population that these numbers are supposed to be representative of. So we would compute the mean, or the average, we could also call it. That, as I said, we were taught to do this back in elementary school, way back, 2nd, 3rd, 4th grade. We were taught the first time how to compute an average. Now, the new thing in this course is that we do not only compute this average, we put an interval on it. That's as difficult as it is, right? We put an interval on the average to include the unknown, the uncertainty, the variability, the randomness of this average. And specifically what we do is that we compute the standard deviation of the same numbers. So we would have some numbers. We would have computed the mean and the standard deviation. I would take some number that I take from, let me take a specific of it, then I can show you in the 95% confidence interval. I take the average plus minus the maximal error, as we called it. Another way of saying it, I take the average plus minus twice the standard deviation of the average. I say twice. Why do I say twice? Because this number, the t, may sometimes be, if n is large, that is at least 30, then this t 0.25 is approximately equal to z 0.025, which is actually 1.96. So even though this t thing might seem a bit abstract, I mean, we can think of this t number as the number 2. I mean, that's the way of remembering it. That's the way of having the gut feeling about this. Basically, we take the average plus minus twice the noise of the average. I mean, that's just saying the same thing in different ways now. Let me be a bit more precise now. This is the method as you can use it. This is the operational part of it. Compute the average, compute the standard deviation, S, and combine the numbers like this, and you have an interval with the mean in the middle and something on each side of the mean, right? Now, what is the thinking that actually justifies this? Well, it comes here now. So it's a kind of a mathematical proof, although not exact in this way. I'd like to convey more the thinking than the actual details of the math. The thinking is the following. When I use up here a single average, I mean, I have some numbers, I compute the average, that's what I'm going to use in my company or in my research or in my society. If I'm the health authorities in the society, I may look at an average of how it goes with some illness, and then I use that in my recommendations to the people in the country. Well, being intelligent about this, one average coming out of the numbers, I have to do a little twist here. I do the twist that in my writing here, let me try to do it again to be a bit more precise. I do the little twist that I assume this average not to be the one and only average in the world. I'm considering my individual average, which was up here, to be only one possible outcome of the experiment, right? Maybe the experiment, the study, would have come out differently. That's the intelligent part of it, that we allow ourselves this abstraction. We acknowledge the fact that our single average is not the global truth of the world. If someone else did the same study tomorrow or in another country or in another city, they would come up with a different average. Of course, why should they come up with exactly the same? Because there are randomness, there are noise, there are variability in the system. So this is what we acknowledge. How do we acknowledge that? Well, here it goes. The first thing is that we think of this number in this justification of the confidence interval or the explanation. We think of the average as a random thing, right? It's only one possible sample we have made out of many possible samples. That's the sample distribution thinking. What is the average going to be used for? Well, the average is going to be used as the guess of the underlying but unknown mu. The truth. Mu is the truth that we are seeking information about by looking at the numbers, by looking at the average. So I should be concerned with the difference, the deviation between what I compute in my average and the truth, mu, that the average is going to be used as an estimate for, right? This difference I should be concerned with. Am I close to mu or am I far away from mu? That's basically what makes us intelligent. Can I say something about this difference between, you could say this is the data, this is the truth. I should be concerned with this number. What can I say about this error that I'm making, you could also call it? This is the error I make when I look at data. This is the difference between my data and the truth. I have to acknowledge that it will always be there. The good news is, and that's some of the theory that we learned last time, the good news would be that the average, or the mean, you could say, the average, on average, is true. So that means the average is a good number to use as a guess from mu, because if I do it many times, on average, I would as many times be on one side as I will be on the other side, and on average, I would hit the right thing. So if I'm using my arrow at the dart or at the skive, again, target, thank you. I didn't remember that last time either. So I would, on the average, hit the center. On the average, I will hit the center. The big question is, will I hit the center in a narrow way, or will I hit the center in a spread out way with the way I compute an average? And what is this? That's the noise in the system. This is basically, what is the variability of this thing, of the average? And in fact, using the variance rule, since the mu is just a constant here, it's not random, it's the same as the variance of the average. The variance of the average is the theory that I showed you last time. This would be this number, and then if sometimes, this is just a theoretical result, I would have to say that the variance of x bar, we would plug in the estimate of this when we're going to use it in the formula. So, not using the true one because I don't know it, but I can compute it from the numbers. So, this is why the error that I make in using x bar for mu is something that is spreading from minus to plus with a standard deviation of approximately, now I say approx here, approx, at least, if n is at least 30, let me use that as the example here, then we already know, and that's the big thing, the big news is here, there's the central limit theorem there, where we can use the normal distribution or the t-distribution for this variability. So we not only know the mean of the error we make, and the variance of the error we make, we also know the distribution. The distribution to be used to put probabilities on what we know is either the normal or the t distribution. That's what we saw last time. So I can use, and basically in our understanding of this, I mean, it doesn't make a difference whether it's a normal or a t. It's a distribution, more or less, that within plus minus 2 have most of the distribution. If it's the t, we need to go check whether it's exactly 2. Maybe it's 2.1, 2.2. We have to go check it. But in our thinking of this, it's the same thing, right? So in our understanding, it doesn't make a difference whether we use the normal or the t. Slightly different curves, but basically the same shape. So if we go 2 standard deviations on each side of 0, that's what we have seen from the standard normal or the t. 1.96, sorry. Then I have the area in which this one will be in 95% of the time, right? And that's the confidence interval, in short. That the error we make will be plus minus this one, because this is the standard deviation of the distribution of this. The sample standard deviation, so I basically just use this thing. Now, and if, I should say, if n is less than 30, instead of using 1.96, I use t 0.025 with n minus 1 degrees of freedom. That's, I already said that previously. That is the concept of the confidence interval, right? We use that we know the distribution of the thing that we are using, the average. Such a confidence interval can be constructed for all the things that we compute out there. We are going to see a number of these in this course, and many more are there than you will see in this course. This particular confidence interval is just for the mean, right? It's an important one. It's probably the one that is used the most, but there are many others out there. That was the confidence interval. Any questions on that repetition? It's an important tool. The confidence interval, if I may, by the end of today and by the beginning of next time, I'll do another repeat of the confidence interval, but I will then link it to what we're going to learn today, which will give us yet a new and maybe the best way of understanding and thinking of the confidence interval, so you can look forward to that. Let me say the very formal interpretation of this would be that the confidence interval as a method, if we see it up here again, the confidence interval as a method is a random thing from sample to sample, right? It has the average in the middle, in the center, and then it uses the computed standard deviation to find out what should the spread be of the confidence interval. And then the n, the size of the experiment, plays a role. And the confidence level, the alpha, plays a role. But if we look at it as a random thing, it's like it will change position from time to time if we did many experiments in the same setting, right? What would happen here? The confidence interval would change from time to time. It will change position, it will change width, because the s will change also, right? So it will be like a random interval from that will sort of go like this. How about the truth, the mu? The mu doesn't change. The mu, the truth, is what it is. But the random interval has the property that in 95% of all times, this is the frequential way of looking at probabilities, in 95% of all times it will include the true value. And the way we work with it in practice is to hope, believe, assume that in the given case we have the true value, knowing that we might be wrong, right? There's a slight chance, risk that we're wrong, but in our practical work with this, we say we put this interval on, because the only thing, if we want to be 100% sure, how far out should we go in the distribution to have 100% of the probability mass? Infinity, all the way and on the other side. So, wanting to be 100% sure is the same as saying, I know nothing, right? The value could be anything. So that is of practical no use at all, right? So 100% sure is in the everyday practical life useless, meaningless. We have to accept the fact that we cannot be 100% sure. We may only be 95, 99% confident. Otherwise, it doesn't make any sense for us. That's a fact of life we have to face. One of many unpleasant facts of life. That was the first part.